Okay, hi guys. So in this lecture, we'll be discussing on phase equilibrium. So let's get started with phase equilibrium. So we have H2OL getting converted into H2OG. Okay, so delta Ng for this reaction would be moles of gaseous products formed minus moles of gaseous reactants which were consumed in the reaction. So 1 minus 0, which is 1. Then if we talk about H2OG converting into H2OS, then delta Ng would be minus 1, and Kp equals to Kc into RT to the power delta Ng. We have discussed it so many times. So let's discuss the SI units or for this. Equations of pressure is measured in atm. Concentration is measured in mole per liter. Then temperature is measured in Kelvin, and R or rate which is we saw this R and P equals to nRT equation as well. So that is the same R, so it is nothing but 0.0821 atm liter over mole Kelvin. Okay, let's see some example. We have 2 Ag reacting with Bg forming 2C. Okay, so temperature at which this occurs is 500 Kelvin. Okay, so Kc in this case would be concentration of C squared, concentration of divided by concentration of A squared into concentration of B. Okay, so in this case let us look at the graph. So the graph is something like this. Concentration with time looks like we have 4m from which concentration of A started, then we have 2m from which concentration of B started, and we have 0 from where concentration of C started and it reached 3m. This is nothing but 3m. Let me draw it again. This is 3m. This is concentration of C, and concentration of B after time converges to 1m. So this is the equilibrium state. Okay, this is the equilibrium state. Okay, so at equilibrium we can have that concentration of A would be, so this is at equilibrium, concentration of A would be 3, concentration of B would be 1, and concentration of C would be also 3. Okay, so from here we can calculate the Kc. Kc would be nothing but Kc would be concentration of C, which is 9, 3 square, and 9 into concentration of B is 1, so Kc would be 1. Now if we have to calculate Kp, Kp would be nothing but Kc into RT to the power delta Ng. So for now delta Ng would be 2 minus 2 plus 1, which is delta Ng would be minus 1. Okay, so the Kp would be Kc into R 0.082 into temperature is 500 Kelvin to the power minus 1. So we can calculate easily this Kp value. Okay, Next, let us see the relationship between Kp and Kx. Relation between Kp and Kx. So let's suppose we have A moles of A reacting with B moles of B and forming C moles of C plus D moles of D. Okay, so partial pressure here would be equals to mole fraction of A into total pressure. P is the total pressure and Pa is the partial pressure. Okay, so we know that Kp is partial pressure of A into partial pressure of C time on raised to the power C partial pressure of D. This is Kp. Okay, and this would be nothing but x times A into total pressure to the power C, x times xb into total pressure times D divided by xa. This is x C and D rather, not A and B. C and D xa to the power A multiplied by xb into p to the power B. Okay, so we can write that this is equals to xc to the power C multiplied by xd to the power D divided by xa to the power A and xb to the power B, and pressure the power will be C plus D divided by A plus B. So just rewriting here. So pressure is C plus D minus A plus B. Okay, so we can write Kp as this is nothing but kx times p to the power C plus D minus A plus B. So this is nothing but Kp equals to kx into p to the power delta ng. Okay, and some interesting fact to note here that if delta ng equals to 0, then Kp would be equals to Kc to be equal to Kx. Okay, now let's look into another concept, which is reaction quotient. Or Q. Okay, so this may not be at equilibrium. Okay, so Qp is nothing but Pc to the power C and multiplied with Pd to the power D and partial pressure of A and B respectively raised to their respective powers, and Qc would be again the same thing, but to note here that the Qp would be equal to Kp if the reaction is at equilibrium. Similarly, Qc would be equal to Kc if the reaction is at equilibrium. So this is at any point of time in the reaction. This is a general way of representing Qp and Qc, where Pc is partial pressure of gas. For example, we can write Px in general, that Px is partial pressure of x at time t, not necessarily at equilibrium. Okay, similarly Py would be concentration of gas A at time t not necessarily at equilibrium. Okay, so this is px and py. So sorry, it's not py. This is rather concentration of y. So this is concentration of gas y at time t not necessarily at equilibrium. Okay, so we can write that if q is less than k equivalent, then graphically we can demonstrate that q is here and k equivalent is here. So we can write that then reaction proceeds in forward direction. Okay, and if so, this means that more conversion of reactants into products. Okay, and if q is equals to k equivalent, then we can graphically show them as q is equals to k equivalent. Okay, and this means that reaction is already at equilibrium. Okay, and the third case is obviously if q is greater than k equivalent, then we can write that q is more than k equivalent, then reaction proceeds in backward direction. Okay, so this simply means that more conversion of products into reactants. Okay, so more conversion of products into reactants Okay, so this condition can actually be achieved when you remove A or B or you add C and D in the reaction. So either you add more C or D in the reaction, or second, if you remove A or B from the reaction. Okay, and with this we come to the end of this lecture. In the next lecture we'll be discussing on types of chemical equations. Till then, good luck and goodbye.